And we're going to use cross products this chapter it comes up when you're dealing with torques. It comes up in next semester physics when we deal with magnetic fields, and it comes up in Calc 3 if you get that far, and if you do a fluids class, it'll come up quite a bit there. Anytime you deal with rotational motion, often you'll deal with cross products. And they have a number of different applications, but we're just going to use it to calculate torques. So remember I introduced the right-hand rule last time, where we can use the right-hand rule to find the direction of a cross product. So for example, I cross J. I like to do it this way, where I let my fingers go in the direction of I, of my right hand, because we're dealing in a right-handed coordinate system. They fold towards the direction of J, and then your thumb gives the direction of the cross product. In this case, I cross J is positive K, and J cross I. Fingers in the direction of J, they fold towards I, so your thumb goes in. You know which direction your thumb goes because they go in the direction of the first vector and then fold towards the second vector. But notice that I can't do that here. It would fold towards negative I if I did it that way. All right, so you can also do, for example, J cross K and K cross J. Try J cross K here just for fun. What is the direction of J cross K? First of all, you know it has to be orthogonal to both J and K, so it has to be either plus or minus I. Which is it? Is it plus or minus I? It's plus I, right. So fingers in the direction of J. I don't know if it goes this way or that, but it has to go this way in order to fold towards K. And so it's going to be plus I. J cross K equals plus I. And K cross J equals negative I. All right. The right-hand rule will come up a little bit later. And again, if you learn to do cross products using the matrices, has anybody done it that way, where you line up the vectors in a matrix form? Okay, well, if you haven't, don't worry about it. Let's just do it this way. But if you do know how to do it that way, that's fine. All right. And you can expand this to do 3 dimensions. So you can have your, I can have vectors with I, J, and K components. So I'll try to keep it a little simpler just for the algebra. Right, we'll do some examples of that with torques. So what is a torque? When I say torque, what do you think of? Cars? Oh yeah, they have engine torque. That's because they have a rotating axle that comes out, or a rotating shaft, and so you have a certain force exerted over a certain moment arm or a radius. What else do you think of when you think of torque? I'm thinking of something. Maybe I should just tell you what I'm thinking of, right? Like a torque wrench, right? You ever use a torque wrench? A torque wrench tells you how much you tightened a bolt, and you put in a certain force over a certain length of your torque wrench, and that gives you your torque. Has anybody ever read on the torque wrench what's it measured in the British system?
Kips.
Huh?
We measured kips.
What's a kip?
Yeah.
I've never heard of that.
Measure bolts and stuff like that. It's a hydraulic system that measures in kips.
Oh, okay. I've never heard of that.
Yeah. That's how we torque bolts. But the hand wrench and stuff like that is, I don't know.
It's in what? Normal people lingo. Foot pounds, right? Foot pounds, you ever seen that on a torque wrench? Or sometimes you'll see it in Newton meters, which is the SI unit for torque. It's just a force that's applied a certain distance from a rotation axis. And I'll define that in just a bit. A torque causes what? What type of motion? Rotation. So a torque causes rotation. And it's useful to describe torques just when, well, we'll apply all the stuff that we did with Newton's second law to torques as well. Because Newton's second law extends to rotational motion. And so chapter 3, where we dealt with Newton's second law, will come up again in this chapter. Just like forces cause cause acceleration. Torques cause angular acceleration. Remember, we call it acceleration A and angular acceleration alpha. And so, similarly, as we thought of linear displacement, we then thought of angular displacement, x to theta. Where we have linear velocity, we now think of angular velocity, omega. Where we had linear acceleration, we now think of angular acceleration, alpha. Where we had force, now we can think of an angular force, which is going to be our torque. So this is the Greek letter tau, and it is the symbol that we use for torque. And you can think of torque as an angular force. Just carrying along in this stream. Now, we don't call torque an angular force. That's why I put it in quotes. So don't go off telling people that a torque is an angular force, because that's not really an official term. But we can think of it in that way, that it's a force that causes rotational motion. Right, here's a wrench. Now, I can describe vectors R and F. So I have a vector here, F, and then I also have a vector R. Then I have an angle between them. My torque can be found with the cross product. It's going to be R cross F. And as we saw before, the magnitude of the torque is going to be RF times sine of theta. And that just comes about from the definition of our cross product, that the cross product of A cross B, the magnitude of that is AB sine theta. Remember, we're multiplying the component of our one vector times the component of another vector. That is what? Parallel or perpendicular to the first vector in the cross product. Does the cross product take the product of two perpendicular or two parallel vectors? Two perpendicular vectors, right. So that's in contrast to the dot product, which took two parallel vectors. Remember how the dot product came up when we were doing work, because we want to know force and displacement in the same direction? Well, now we want to know force and moment arm, which is R, in perpendicular directions. So this sine of theta effectively gets rid of all other components except for the perpendicular component of that force. Now, if the angle between F and R is 90 degrees, then the torque is just R times F, because the sine of 90 is equal to 1. And that's this example right here. So I have my R vector, and then I have my F vector, and the sine of 90 degrees. This is, does anybody know what this picture is, by the way?
A door.
It's a door, thank you. So this is a door, and it rotates about this axis. And notice that if I push on this door in this direction, in the force, it causes rotation. But what if I push on it in this direction? So what if I have a force vector that pushes on it in that direction? What kind of rotation will it cause? It's going to cause no rotation at all. So you all understand torques, right? Every time you open the door, you understand torques, because nobody's going to go up to the door and push on it in that direction. You just look like an idiot, right, if you pushed on it in that direction. Because everybody knows that in order to produce a torque, that angle has to be something greater than 0 degrees, right? And actually, the best way to close a door is to apply a perpendicular force, because that provides the greatest torque. It makes that sine term go down to 1. That sine of 90 is equal to 1. So every time you open a door, you sort of think about this torque problem, right? And what's the best way to apply a torque? Maybe you will know. Now, the SI unit for torque is a Newton meter. Like I said, if you have a torque wrench, it usually has either foot-pounds or Newton meters on it. Often they have Newton meters, actually, the ones that I've seen. Have y'all seen torque wrenches before? Anybody seen a torque wrench? Does that have Newton meters on it? Do you remember? I had foot-pounds? Yeah, okay. Okay, wow. Anyway. You can sometimes see this in the British system in foot-pound. But that's the same, right? It's just distance times force, and a pound is a measure for force. Just as we had last time, clockwise torques are what? Are those positive or negative? Those are negative, right? This is our notation that we take. And then counterclockwise torques are what? Positive or negative?
Positive.
They're positive. Right. So we'll take those as our positive and negative. I missed something on the previous page? Well, let me see something. I think I'm missing something. No, let me just write it in. We're going to have a whole chapter, and this isn't in your book, but we're going to add it in on elasticity and equilibrium. I think I sort of have part of it done. I wasn't able to finish it, but when we talk about an equilibrium situation, what was one requirement to have a system in equilibrium? Think chapter 4. What was the requirement to have it not accelerate? To have it in equilibrium, to not move? What had to be true?
The net of all should equal 0.
Right, the net what?
Torque,
The net force, right. Yeah, so in order to have equilibrium or a static situation, we said that the sum of the forces had to be 0, but it's also true that what else has to be 0? The sum of the what? Like here. Rhymes with dork. Come on, what rhymes with dork? Torque, right. So,
Torque does too.
yeah, the porks have to add up to equal 0. So for static situations, it's true that the sum of the forces equals 0, and these are vector quantities, and it's also true that the sum of the torques equals to 0. And so we'll apply that later. We're going to do a little bit in this chapter, but later when we get into chapter 9 or 10, we'll get into this as well in more complicated situations. When we look at structures, and we can add up all the forces that are acting upon them, and then also add up the forces. And what that does is it allows us an extra set of equations to work with to determine various unknowns that we may need. So it's pretty useful. Let's do a simple clicker question here. I think you have a homework question that's similar to this. In this problem, you want to calculate the net torque. All you're doing here is just determining the torque and adding them up, taking the clockwise to be negative and counterclockwise to be positive. So remember that torque, the magnitude of our torque is Fr sine theta, and clockwise torques are negative and counterclockwise torques are positive. In this case, your bar, which we'll take to be massless, or it doesn't matter actually, is rotating about the point C. So it's rotating like this, about that point, in some direction. We don't know what direction it's rotating. Let's see, I'll rewrite the options up here so you can see them. Let me go and start. So those are your options. They're all in Newton meters. What is the net torque? So this is similar to what we would have done before when we found the net force, but now we're dealing with torques instead of forces. Y'all want your exams back today, right? Y'all finish this up. I'm running my office teacher. If you finish this, go on to the next problem.
The middle one doesn't count because it's put it in the bulk. Rounding differently, you probably would using some of the.
All right, just a few more seconds. Stop at 6:20. Let's see, is C right? Pretty sure that's right. I'm gonna go and mark it. We'll work it out. So I should be able to look at this and tell right off that it's counterclockwise because this force is bigger than this force, and not only is it bigger, but it's also at a bigger angle, so it's more towards the perpendicular. So even if they were the same forces, this force would be providing a larger component that's perpendicular to the moment arm. It's rotating about this axis, so what is R for the 30 Newton force? Is 0. Now R is the distance from the axis of rotation to where the force is applied. And for that 30 Newton force, the axis of rotation and where the force is applied is the same. So it would be like wanting to rotate my arm about my elbow and applying a force at my elbow. That's not going to cause my arm to rotate. In order to cause my arm to rotate, I have to apply a force here, which is what your muscles are attached. Not at the joint, but just below the joint to cause your arm to rotate. So that 30 Newton force will provide no torque. And then it's just a matter of adding up the torques. Does this force cause a positive or negative torque? Or is it clockwise or counterclockwise? It's counterclockwise, right. So that force will cause this bar to move like that, which is counterclockwise in that direction. So that is a positive torque. I'll call it plus tau 1. And this is a negative torque. So the sum of my torques is torque 1 minus torque 2. Torque 1 is going to be 25 newtons times 2 meters. That's this distance right here, times the sine of 45, minus 20 newtons, 2 meters. That is this distance from where the force is applied to the axis of rotation, times the sine of 20. Does that give me 22? Anybody? Is that 22?
21.4 is what you're talking about.
Oh, 22. All right, so 22 Newton meters counterclockwise. I know that it's counterclockwise because it's positive, and counterclockwise direction is positive. All right. So that's like finding the sum of the forces as we did in chapter 3 and 4, or chapter 4 rather. But instead we're finding the sum of the torques. Let's try this next problem. It's a little simpler. What happened? Yeah. Okay, here we go. So Chad, hey, that's me. Did y'all know that was my name? My name is actually Chadwick Hayward Young. Somebody once told me that it sounds like British aristocracy. Do you think that's the case? My parents tried to give us all fancy names because we weren't really fancy people, but they gave us real fancy names. So, like my brothers, their middle names are also Hayward, which it's my dad's name. But anyway, so it stands on a 5-meter long board, 4 meters from the pivot point as shown in this figure. There's a mass 75 kilograms, and then Kaisa, that's my wife. Did y'all know that? That's her name, Kaisa. She has a mass 60 kilograms. Where can she stand to balance the board? So I have a mass of 75 kilograms down here. Where can she stand to balance this off-kilter seesaw? I'm just going to move it down to the options. Yeah, I'm sorry, you don't have your book. Okay. Where can she has a smaller mass, where can she stand to balance this board? So I have to go back down. Okay. Stop at 110. 110. Very good. So there's nowhere that she can stand in order because she has a smaller mass. In fact, in order to balance this board, you would have to have somebody down here that was, what, 300 kilograms. That's a big person, 300 kilograms. All right? But in order to balance the torque, somebody 4 times the mass because it's 1/4 the distance. All right. Let's look at this problem. This is a simple statics problem. As I said, we'll do some more complicated statics problems where we have to look at the sum of the torques and the sum of the forces later. But in this case, I just have this seesaw and these 2 little kids on it, and or man and a woman, I guess. The man has a mass of 100 kilograms. This is the guy. And the lady has a mass of 50 kilograms. And I just want to know what is the length x here. What is this equal to? We did this in lab yesterday with the balance beams. It's a simple torques problem. I just say the sum of the torques. I'll call this torque 1. I'll call this torque 2. The sum of the torques will be, which one is positive, torque 1 or torque 2? Yeah, torque 1 is counterclockwise, torque 2 is clockwise, so it's going to be torque 1 minus torque 2. This one's counterclockwise, this one is clockwise. That's going to equal 0 if it's balanced, so the sum of the torques equals 0. And this is going to be FW1, or M1G, times 2 meters, minus m2g times x, and that has to equal 0. And then I solve now for x. The g's cancel out. X equals m1 times 2 meters divided by m2. That would be 50 over 100. Which is 1 meter. So he has half the mass, so he needs half the moment arm. Or twice the mass, so he needs half the moment arm. Right. We'll get into some more complicated problems, and honestly, on your quiz, you might see some multiple choice problems like this, but in your free response, they'll be more complicated, flywheel spinning and stuff like that. Okay. But this is pretty simple, right? This is pretty basic, I think. Now, if the mass, actually, we're going to skip that part. We'll get into that later. So let's just skip the forces stuff. All right, we'll come back to that stuff. But first, I want to explore a couple of other ideas. So as I said, Chapter 8, said this before, Chapter 8 is really a compilation of all the chapters that we've done so far. So before we did energy, before we did momentum, we're going to see all that stuff in a rotational frame. So for the kinetic energy of rotation, if you remember, with kinetic energy, we had kinetic energy was equal to 1/2 mv squared. Actually, let's stop here. I want to give you your tests back, but I couldn't find them right off. Can I have another few minutes to go into my office and find your tests? Yeah. They are in my office somewhere. I thought they might be in here. You don't want them back, right? You want them back? You might not. You should get them back. Just give me a couple minutes, okay? I'm very sorry. I know it's been Give me a few more minutes. Let's do a little bit of this kinetic energy stuff, okay? And then I'll hand back your exam. Sorry, Scott. Would y'all rather do this or listen to Scott play? No, that's a rhetorical question. Did I tell you all my roast beef joke? No, you want to hear it? This is kind of potty humor, okay? So if you're offended, I'm sorry. But, yeah. What's the difference between roast beef and pea soup?
You can roast beef, but you can't pea soup.
Ah, Scott.
What was it?
That's it. Your anybody can roast beef. You get it? But nobody can pea soup. Right, sorry. What lies at the bottom of the ocean and twitches? nervous wreck. Okay. All right, kinetic energy. So anyway, we had kinetic energy as 1/2 mv squared. And we can relate this to our angular velocity, where we'll express it in terms of omega instead of v. And actually, we're going to express m not in terms of m, but something we call the moment of inertia. And I just want to step through this derivation, and we'll do some derivations for moments of inertia next time. But let's say that we have this rotating body, say it's a disk or whatever. It's rotating about this axis, and we can imagine that it's made up of like an infinite number of little infinitesimal elements. So it has a whole bunch of little pieces that we use to make up this rotating body. These are called differential elements. Have y'all talked about this in calculus? Differential elements? No? Well, whenever you put a d in front of something, that's basically a differential element. So if I say, the derivative of something with respect to t, I'm making t, that interval t, go really small. I'm making it really small, and that's a differential element. Now, each element has a different linear velocity, right? As I have all these little pieces, each of these little pieces is going a different speed. So each of them has a different kinetic energy. And what I want to do is to calculate the kinetic energy of each of those little pieces, and then I'll add them all up. I'll do like this huge summation. And that summation is called a what in calculus? What's a summation? I mean, it's either a derivative or an integral, right? That's really all you do in calculus right now. What is it? It's an integral, right? So whenever you're doing a summation, that's just an integral. An integral is just a summation. However, each of these has the same angular velocity, so we can simplify it just a bit. Let's see, so my kinetic energy of each piece is equal to 1/2 mv squared, and my v is equal to omega times r. So I can say then that the kinetic energy equals 1/2 times m times omega r squared. R, I can express this in a slightly different way. Well, no, we'll come back here in just a second. So the angular velocity is constant for each differential element. So then I can find the total kinetic energy with a summation, and it's going to look like this. I'll have 1/2 times the summation of mr squared. This is going to be the mass and the radius for each individual element. Because if you remember our picture that we had this rotating disk, or whatever the shape is. I have each little differential element. Each of them has a little mass, mi, and each of them has a radius from the axis of rotation. That's ri. So say, for example, let's say I take this element. It has a radius, ri, and it also has a mass, mi. So each differential element has a different quantity for that mr squared. So that's going to be my summation. However, each of them has the same omega. I'm going to let this summation, I'm going to break it into an infinite number of pieces. So I'll let I go from 1 to infinity. Now, for linear motion, we use the mass to describe the inertia. Remember that inertia, it described how difficult it was to put something into motion. So if you had a real big object, it was very difficult to put it into motion. It had a lot of inertia. Or it was really difficult to stop it from moving. You had to put a large force on it in order to stop it from moving. In a similar way, for angular motion, we describe the moment of inertia. And this describes the inertia of a rotating body. And so for a rotating body, the mass isn't really the only thing that's important. It's also how that mass is distributed. We'll talk about that a bit more next time. And we're actually going to calculate this moment of inertia for a number of different bodies. Can I go down for just a sec? Hang on just a second. What's this? It is difficult to change the rotational motion of the object. All right, next time we'll derive some moments of inertia. We're going to get into volume intervals, and you'll actually be responsible for doing some of those for the next quiz that I'll show you, but I'll wait till next time. They're fairly involved. Let me go ahead and hand back your test. Well, what did I do with them? Oh, there they are.
Find them again.
They were right on top of my desk. Like I set them out there yesterday, so I wouldn't forget them this morning. All right. I don't think there was a curve on this.
Do you remember what you had on the middle? Oh yeah, no curve. There's no curve.
Bryce, Chris, out. Grab me when you get it.